Hi everyone, welcome to this week's Scholarship Chemistry tutorial video. This week I'm taking up question 2b from the 2016 exam. In this question, nitrogen dioxide, or NO2, we know it's a brown gas, and it's in equilibrium with a dimeric species, dinitrogen tetroxide, which you see in the first equation here I've written out. So this is something you have to figure out for yourself. From the information you're given, can you write out the equation? There's a second equation we got to be able to write out too, and that's the reaction of dinitrogen tetroxide in combustion with hydrazine. And this rocket fuel produces two things, nitrogen gas and water. So I've made sure to balance it as well. And they haven't said it's an equilibrium, it's a combustion reaction. We know that's a forward reaction, so I just have a forward arrow in that reaction, but I have the double-headed reversible arrow in the top equation. So remember your arrows. I also have states of matter, and okay, so I've got my two equations there. I'm ready to go to look at the question. So what is the question? The question is to discuss how enthalpy and entropy affect the dimerization equilibrium. So the reaction between nitrogen dioxide in equilibrium with dinitrogen tetroxide. So if we need to discuss how enthalpy and entropy affect the equilibrium, we need to break it down a little bit. So the things we need to answer are, with enthalpy, which direction is exothermic? Is it the forward or the reverse reaction? To answer this, we're going to have to actually calculate it with the data tables we've been given. What about entropy? Is there a decrease or an increase in entropy in the forward reaction? Just looking at that, you might have a hint already, or a feeling already what it's going to be, but we'll look at that too. And we got to put it all together. Okay, so the first thing we should do is calculate the enthalpy change of the forward reaction. We're going to use a familiar equation where we take the sum of the enthalpies of formation of our products and subtract from that the sum of enthalpies of formation of our reactants. This is a quick process since we only have one product and one reactant. And in the end, we get an exothermic energy change of negative 57.2 kilojoules per mole. The main point is that it's exothermic. That increases the favorability or likelihood that the forward reaction is more spontaneous or more favored. So we know the forward reaction is exothermic. This increases the favorability of the forward reaction, i.e. it's more likely to happen spontaneously than the reverse. But we do need to consider what's happening with the entropy change in the forward reaction, because that plays a huge part as well in combination with the enthalpy change in determining whether one reaction direction is favored or more likely to happen spontaneously. So let's look at the entropy change. Actually, the forward reaction is unfavorable from an entropy point of view because we're going from 2 moles of reactant to 1 mole of product. So the entropy change is decreasing, it's negative. This is not favorable. So in summary, what do we know? In this table here, we see that from the forward reaction point of view, it's favorable from an enthalpy point of view because it's negative or exothermic, but it's unfavorable from an entropy change point of view because it's negative. However, in the reverse direction, it's unfavorable from an enthalpy point of view, where it is favorable because entropy is increasing in the reverse direction, going from 1 mole of product to forming 2 moles of reactant, right? So, really, which direction is favored in this equilibrium? Well, it's hard to tell. It depends. It really does depend. And what does it depend on? Well, if we think back to what Gibbs free energy equation tells us, it depends on, well, how high or low the temperature is. So let's look at the scenario of the forward reaction. The forward reaction has a negative enthalpy change and a negative entropy change. So if we look at the third row in the table, we see that for the forward reaction to be spontaneous, the temperature needs to be very low. If it's too high, it's going to be non-spontaneous. So this is what you need to write. It really depends on the temperature. So that's the full solution, really. It's not a clear black and white answer in the end. It depends on the temperature that the forward reaction is undergoing. So what are the conditions that this equilibrium is in? So that's the answer to the first part. Let's move on to the second part. Okay, in part 2 of this question, we need to discuss why this rocket fuel mixture is suitable as rocket fuel, linking it with the data below. So we're going to have to do some calculations. As well, we're probably going to have to discuss the magnitude or size of these numbers. The first thing we're probably going to have to do is calculate the enthalpy change. And then we're going to discuss the entropy change. Let's make some predictions first. If this is rocket fuel, ideally, to ensure that it reacts spontaneously, the rocket fuel mixture should react such that the enthalpy change is extremely exothermic. So we should get a really negative delta H value. Also, the entropy change should be extremely positive. We want to form more stuff because that helps generate thrust. And in most cases with rocket fuel, you're generating a large volume of gas. And I can see on first sight looking at this equation, yeah, one of our products is 3 moles of nitrogen gas. So I think on first sight that it looks like entropy change is favorable, but we got to do that enthalpy change calculation first to also confirm that. Now there are 2 equations we could use. The first one is familiar. That's the equation we used to solve the enthalpy change problem in the first part. So let's use that for this part, and we get an answer of negative 1,254 kilojoules per mole in the end. If I were to use the second equation instead, if that's your favorite equation and you use that, you'd get a slightly different answer, but it's still extremely exothermic. So from the enthalpy point of view, this is favored. The enthalpy of a reaction is very negative, so there is a large amount of energy released, making this very useful as a fuel from an enthalpy point of view. But what about the entropy change? Before we get to that, why is the enthalpy change so negative? It's because of the extremely strong nitrogen-nitrogen triple bonds and the very strong OH bonds. And when these bonds form, a large amount of energy is released. So that's why it's so exothermic. Now from an entropy point of view, more and smaller molecules are being produced. We have 3 moles of nitrogen gas, 4 moles of water molecules, and this makes the reaction favorable from an entropy change point of view. So we have an extremely favorable enthalpy change, an extremely favorable entropy change. So this reaction is going to happen spontaneously. And that's it. That's the end of part 2 and this question. Thanks very much.